Also have joints that get a little achy when the weather changes, but the older I get, the more I feel that. So, and yes, we are in for a rather sizable April storm. So we'll see if it materializes. Around the coffee pot earlier today at the university, all of the weather geeks were talking about whether we'd set a record. The record single 24-hour snowfall in April is 13.6 inches. I'm hoping we don't set a record personally, but we've certainly had that kind of winter. I'm not going to talk about what's been happening this winter specifically. I might refer to it from time to time, but after having a dialogue with Rob about your meeting and about what your interests might be, what I'm going to focus on are the past, especially in the context of trends, especially the last 3 decades, because those of you that have studied a variety of phenomenon out there in the natural environment realize that as we compile data about things, when we start to see patterns and we start to see extreme measures crop up in our data with some frequency, it really gets our attention. And in my lifetime as extension climatologist here, I've certainly seen that happen. And it seems like with each passing decade, it's been happening more and more. And so I want to talk about that a little bit, but I not only want to talk about what we're measuring as caretakers of the state climate database, I want to talk about coherent consequences of what we're measuring. And some of those coherent consequences may relate to your work. Now, I don't pretend to know a lot about your work. I'm just basically a measurements person and a caretaker of our state's climate database. So it does relate to lots of things. I mean, public health, transportation, agriculture, architecture, water resources, energy systems. I mean, the list goes on and on. But I don't know a lot about those things, but I do know a lot about the measurements. So I would trust that my remarks and the data I show you might provoke in you to make the coherent linkages to what's important with what you do. As a premise for that, I illustrate with the joke about the Minnesota veterinarian, the large animal veterinarian, who was out on his day rounds on the farm in one spring, and he came back and decided before going home to stop at the bank. So he walked into the bank and he walked up to the teller window and he reached in his pocket and he took out a rectal thermometer. And staring at his deposit slip, he said, "I wonder where I left my pen." That provokes all kinds of ideas. And so maybe looking at these slides and these data will provoke ideas in how it links up with important things for you. As laying down a marker, we live in one of the most highly variable climates in the northern hemisphere. We're mid-continental. We're exposed to almost every type of air mass that Mother Nature generates. And as such, we have very sharp and distinct seasonality. But on any day of the year, we can have tremendous, tremendous variation. On today's date, for example, in 1928, it was 83 at Beardsley, and farmers out in the western thumb of the state were thinking about planting their small grains. Why not, if it's going to be that warm and dry? Conversely, in 1975, up at Tower in St. Louis County, it was minus 21 on today's date. So sharply, almost like mid-January. In 1960, Canby out in Yellow Medicine County was having a 1-foot snowfall on today's date. And in 1967, we were having tornadoes down in Faribault and Freeborn County that destroyed some farms and some outbuildings down in that neck of the woods. So roll of the dice for weather on today's date, holy cow, pretty variable. I'm going to talk briefly about recent history and the traumatic and dramatic events and episodes that we've documented in recent history. It's remarkable how it seems like anymore that if we get through a year, if we get through a whole year in Minnesota, without some kind of a traumatic event. It's almost miraculous. I want to talk about the changing features of our environment, but particularly those that are statistically changing the most. And then some of the consequences associated with those, and then a few comments on extremes. The drought of 1976 is noteworthy in my history because it created my faculty position. It's simple. It was so detrimental and so consequential to the Minnesota agricultural economy that Bill Hugh, who was then the vice president on the St. Paul campus, vice president for agriculture and the founder of the Institute for Agriculture, lobbied the Minnesota legislature to create a new faculty position. Then Don Baker, the noted climatologist on the St. Paul campus, came down to NASA, to the Johnson Space Center in Houston, Texas, and recruited me. First time I told him no. Second time he wouldn't let me tell him no. So anyway, that's how I ended up. But we've had quite a run of events year by year. Some of these have been highly consequential, with over $1 billion, over $1 billion in impact. For example, certainly that was true with the '88 drought, which was estimated at about a $4.5 billion impact, and the 1997 spring snowmelt floods, which again was about a 1.8 to a 2.0 billion dollar impact. And we've had all these other particular events. And even last year we had some very significant events. We had widespread winter kill because of the nature of last winter. We had the devastating April ice storm that closed down southwestern Minnesota for a number of days with widespread power outages. And then we had the largest filing of prevented planting claims by farmers in many, many decades. In fact, largest filing of prevented planting since the spring of 1979. So that's a fairly substantial impact there. And what's in store for us in 2014? Well, we hope nothing. But if you look at this laundry list of year-by-year things, it seems like more often than not, something does materialize. In terms of our overall Western Great Lakes climate, the features of our climate that are changing the most are temperature, and I'll show you some examples. The central values, or what we call the means or the median values, are changing, but we're also seeing changes in the seasonal distribution. We're also seeing changes in the extremes and other dimensions of temperature as well. Water vapor, which we measure as dew point, the amount of water vapor in the air around us, has changed remarkably since the 1980s, and I'll show you some illustrations of that. And then precipitation. And precipitation has become more amplified. In general, we've become wetter. Our mean character has become wetter, but we've also become more highly variable behind that. And there's also been some character change in precipitation. One of the things that we need to be real careful about in public engagement is that when we talk about measures of climate change, that we not talk about them as if they're uniform, because they are far from uniform. And the way this plays out is in areas or geographies where they're rather significant, the communities are paying attention to this, and we're no exception to that. But we also have to acknowledge that there's other areas, there's other geographic regions where, if you will, measures of statistical climate change have not occurred, quite frankly, or they've been very minor relative to what we've experienced. If you take a character of climate like temperature, for example, and you simply examine it across the nation, what you find here by the color shading, which is the light red and dark red values, we happen to occupy an area of the American landscape where temperatures are changing more than other areas of the country. And as a member of the Extension Service for the last 37 years, I can tell you that my colleagues in southeastern US, they don't give the same attention to this issue that we do up here in the Western Great Lakes. Because, you know, it's not as evident in their data. It's not as evident in terms of any observable consequences. So there's disparity, but where it is happening, we are inevitably giving it more attention. Canada now, Environment Canada especially, and Agriculture Canada, are starting to give it a lot more attention across the Canadian provinces. In our state, the picture of temperature across time can be derived from calculating a pooled statewide mean using all our volunteers in the state. We have about 252 currently that go out and make daily temperature observations for us. And if we pool all those and we calculate an annual mean temperature year by year from the late 19th century up to the present, we find that it does have an embedded trend that's upward. It's more steeply upward in the last 3 decades than it is across the 100+ years of record. You'd also note that in recent years we've had a high frequency of individual years noted up here where the mean annual temperature for Minnesota has exceeded the historic 90th percentile. So we've really been skewed in that direction in some individual years. There is a seasonality, there's a seasonal disparity in how strong the warming signal is. In the winter, we see that the warming signal is pretty persistent despite the aberration of this winter. In fact, that's what's so striking. You know, this winter is going to go down as a top 5 from the standpoint of temperature. This winter is going to go down as a top 5 in our state history, which is remarkable in terms of bucking the trend of the last 3 decades. And then it's a little less so in the spring, but we still see a warming trend. Again, less so, but we still see it in the autumn, and even less so in the summer. But we still see evidence for that. Some of the changes in terms of what we call normal or average, location by location, hasn't been like small fractions of a degree, it's been whole degree changes. So Milan, which is out in Chippewa County and is on the Op Jordan farm there, one of our what we call members of the HCN, the Historic Climate Network in Minnesota, because it's essentially been in the same landscape for its entire duration of time. Look how their averages have changed across time. Once upon a time, their average January minimum temperature was a minus 4.3. And now what we call average out there is a plus 3.7. And you can see how these have changed. These are remarkable in a statistical sense, because if we go back in time, we don't see the numbers changing by this magnitude earlier on in our history. We've also seen prolific positive change location by location in what we call average, whether we're talking about average monthly maximum temperature or average monthly minimum temperature or average mean temperature. The change is in the positive direction for the most part, and in some cases the change is very amplified in whole degrees. So you can pick a spot on the Minnesota landscape and look at this. This is what it looks like for Austin, Minnesota, when we transitioned from using the 1971 to 2000 time frame as calling that the normals or the averages for Austin, and we moved it to 1981 to 2010, which we're obliged to do by law, by the way, to use the 3 most recent complete decades to calculate our normals. There it is for St. Cloud. The same patterns, the same seasonality is embedded, the same positive direction is embedded. There's Wilmer. You can see that it's pretty pronounced. It's a pretty what we call recognizable imprint of positive change in the statistics. There's Fergus Falls. You can go to our website and get access to these data if you want to look at them for yourself. Maybe you have a region of the state that I'm not representing here, but you want to see. how amplified it's been there. And you can go to climate.umn.edu for access to the complete state database if you want to. Now, having shown the data, I think more importantly is to associate the changes in the data with observed consequences. And being part of the University of Minnesota St. Paul campus, where we have 11 different academic units operating there, it's been easy for me to cross-disciplinary wise look with other researchers at what some of the measured consequences have been. So we note that our soils and lakes are frozen for fewer calendar days, typically. If we do it decade by decade, we see that happening. We see that under systems of minimum tillage or no tillage at all, that our plant residues are breaking down faster in the field thanks to a more favorable environment for biological activity. We see our farmers are applying nitrogen much later in the fall season because they're having to wait for soil temperatures to cool down, and sometimes that doesn't happen until November or later. We see a biological consequence in that some organisms that formerly did not survive our winter, or at least survive our winters with much population, now they're surviving more frequently. And so we see evidence for that. Fewer heating degree days overall, increased freeze-thaw cycles. So once upon a time in Minnesota, we'd go below 32 and we'd stay under the 32-degree mark for day after day or week after week. We had many a winter like that in the old days, but now we freeze-thaw quite a bit, and that's quite damaging to roads. We've seen change in plant hardiness zones, so Minnesota Nursery and Landscape Association sees this as a silver lining because, quite frankly, now for landscaping purposes, they can market more Zone 4 plants. They can even market more Zone 5A plants for landscaping in Minnesota because they're now more suitable to surviving here and doing well here. Longer growing seasons and public health issues, because now we have an extended, much more extended mold and allergen season than we had formerly in Minnesota. Our growing seasons, we're not alone in this. A lot of the states are showing a longer growing season. 9 days. In our state, we've calculated location by location within Minnesota that it's increased between 6 and 13 days most places. We've certainly seen an associated expansion in terms of individual cropping systems. We've seen both a northern and a westward expansion of certain cropping systems because of this. The plant hardiness zones where Zone 4 by the orange here, Zone 4A and 4B by the light violet here, we see in the old system. Now we've got most of the state is in Zone 4. Zone 4 encompasses quite a bit of the whole southern half of the state, and embedded in Zone 4 is Zone 5A now, notably in the Mississippi River Valley and some of the southern parts of the metro area. We've seen lake temperatures, aquatic habitat change. So we all have seen the documentation that the Great Lakes are warming, surface waters of the Great Lakes are warming. These trends are here for Lake Superior. You can see the Lake Superior itself, here the surface water temperature in the blue line, is actually warming more steeply than the surrounding coastal air temperature stations. So we've seen that in play. Loss of ice on our lakes. We see that even our smaller inland lakes, the smaller population of lakes that we monitor in Minnesota, are losing their ice generally earlier, even though we've had some late ice out dates, notably last year among many. In fact, for this year, doing a quick comparison, here's a quick snapshot of the MODIS satellite image at the end of last month over Minnesota. You can see the upper and lower red, and you can see Mille Lacs here. Here's a snapshot of March 27, 2012, which was one of the all-time earliest. In fact, for all of these lakes, 2012 was the earliest of record. So we got Lake Minnewaska here out in Polk County. We got a 108-year record on Lake Minnewaska, and its all-time earliest ice out was just 2 years ago on March 21st, 2012. And then the very next year, last spring, was the all-time latest, May 11. So we had back-to-back years in this 108 year of record where we had the earliest and the latest in back-to-back years on some of these. We also see from the standpoint of the nation's phenological observation network, and in fact that's become even more. Are any of you members of the Minnesota Phenological Network? Anybody here? I would have thought we might have one or two. That's really expanded in recent years, by the way. In terms of monitoring native species, so in terms of budding, leaf out, bloom, etc. Their monitoring networks are showing that in our region here, that the spring onset for these phenological events is occurring anywhere from 4 to 8 days earlier than it once did. And so we're seeing that in evidence across the state in many areas. In fact, you'll notice that the higher latitude positions in our continent, similar to the disparity that we saw in the temperature signal change, the map I showed you earlier, we're seeing that it's the northern section of the country that's seeing the most shift in a lot of the phenological observations in terms of those occurring earlier on the spring calendar. Here in Alec Hodson's record, we have I don't know how many of you know the name Dr. Hodson, but a very famous man at the University of Minnesota who started a long series of phenological observations, was an entomologist on the St. Paul campus. In fact, Hodson Hall is named for him. For this, and you'll have to excuse me because I got to read this. Oh, this is lilac in full bloom. So that's a phenological record circled there of lilac in full bloom. So in 2012, the earliest phenological date for lilac in full bloom took place on April 18th, beating the former record from an early spring in 1987. And then last year, it was May 25th. So in back-to-back years, based on this climate variation we're experiencing, we had a phenological event on April 18 for lilac bloom in 2012, and the very next year, it was all the way out to May 25th. So that's quite a spread there, and that's typical of what we've been seeing. Second feature I mentioned was the water vapor feature. Now this one doesn't get as much attention, or at least we find that the media don't deal with this one as much as the other climate attributes, but it's real, it's episodic. The frequency that we get 70-degree dew points, both here in the Twin Cities and up north at Voyageurs National Park along the Canadian border. I should emphasize, and some of you probably already know this, by definition, meteorologically, a tropical air mass has a dew point of 70 degrees. The air mass is of tropical origin. We don't get those too often, or at least we have a history of not getting those too often. But now we're getting those with greater and greater frequency in Minnesota. We've even had 80-degree, extraordinary, we've even had 80-degree dew points in our state. And they're coming with increasing frequency. I might add, having written the Minnesota Weather History book a few years ago, where I compiled all of the data back to 1807, we have no record of an 80-degree dew point ever occurring in the state of Minnesota until the summer of 1983. It did not exist in our climate record. But since that time, we've started to see an increase in frequency of these things. And as you can see, even the northernmost reaches of the state have had values this high. What's the context for this? That's Persian Gulf humidity. You might as well be over in the Persian Gulf in the Middle East to have a dew point that high. Unbelievable amounts of water vapor. Yes, sir.
Is there any contribution to that from the amount of land planted in corn, or is that probably extends back farther than the dates.
The question is there any substantiation or evidence that some of this might be coming from agriculture, for example, like corn or changes in the vegetative cover? Indeed, a lot of people are studying that, and there is right now within the context of the discipline of agricultural meteorology what we call a working hypothesis that suggests that the nature by which we've changed the management of the Midwestern landscape now puts so much transpired water vapor into the atmosphere during the summer season that it's inflating these dew points. And that does have some legs, although it's not universally accepted yet. Some of the arguments or the counters to that working hypothesis are that we also have to recognize that all the lakes are warming. And as all the lakes warm, they too emit more water vapor into the overlying atmosphere. And the abundance of water vapor emitted now, the increased abundance of water vapor emitted now, especially during the high sun season, by the Great Lakes themselves, is very amplified in the satellite imagery that we've been collecting since the 1970s. Another argument or counter that's made to that is still yet to be sorted out is the northern hemisphere oceans are warming as well. So even when currents or air masses migrate across the North American continent now, normally from west to east, as they come off the eastern Pacific Ocean, they're carrying, if you will, a heavier load of water vapor than they formerly did. But you're right, they're looking really more detailed into landscape feedback and what that means. So it may be that we'll hear a lot more about that in the future. The most immediate consequence of the high water vapor content of the atmosphere is that it inflates the heat index. Now what's that? The heat index is a measure of the physiological effect on our bodies, on the thermal regulation of our bodies, that the combination of water vapor and temperature in the air around us has. And so a 70-degree dew point or higher can take a normal summer day of 85 or 90 degree on the thermometer feel like 105 or 110 or 115. Now, once again, by law, the National Weather Service has to issue a heat advisory if the expected heat index that day is going to go to 105 or greater. By statistical analysis since the 1980s, the National Weather Service has had to issue more heat advisories in our region, and this is the whole Great Lakes region, than it ever has in history. And it's the dew point that's driving that, because as you'll recall, we're not getting that many 100-degree days anymore. We're not sending the thermometer to 100 as much as we have in past history. But what happens is we get all these summers, for example, we've had all these range of heat index values. This one of which I have asterisked here because there's actually, from the standpoint of Minnesota's bragging rights, there's a big story behind that, because on July 19th of 2011, at 6 p.m. in the evening, the Moorhead Observer in Redwood, in the Redwood River, or the Red River Valley, was observing an 88-degree dew point with a 97-degree temperature and giving 134 heat index. That caught the attention of every weather person in America because it was off the charts. And so, you know, the gut reaction when you see that, unfortunately right before the 6 o'clock news is when that goes out on the weather wire, the gut reaction is, oh, the sensors must have gone bad, let's dismiss that. Or, boy, the weather observer's been drinking too many beers, you know, or something. So, but then when we go back and we recheck and we certify all this, we see that that reading is within the range all throughout the Red River Valley. So we submit that to the National Oceanic and Atmospheric Administration certification program, and sure enough, they validate that that is a new North American record. North American record for the highest heat index ever measured, 134 degrees. That was hotter than Furnace Creek, Death Valley that day. So absolutely remarkable. So we got claim now to the North American Heat Index record to offset our claim to the coldest Groundhog's Day in history. You know, minus 60 on February 2nd, 1996. So talk about having two extreme records. That's where we're at. Yes?
Why are we seeing these extremes in humidity so far away from the Gulf of Mexico, and are other parts of the country seeing these changes in dew points?
Yeah, why are we seeing that? Why are we seeing these extremes, again, driven by water vapor, driven by dew point, occurring so far from the Gulf of Mexico? Because you're quite right. A lot of the historic evidence for spells like this in our ancient history comes from following trajectories of moisture from the Gulf of Mexico, where it occasionally does come all the way, you know, up here. And that gets back to the earlier question. Landscape feedback is a good argument that it's local scale feedback that is amplifying the water vapor content of the atmosphere. And it's, bear in mind that what we measure here at the surface is simply a given mixing volume. So what happens, and the reason why so many of these values spike at the end of the day, is the mixing depth of the atmosphere, or what we call the boundary layer of the atmosphere with the migration of the summer sun, starts out in the early wee hours of the morning, very compressed volume. There's little vertical mixing. So what we measure with the hygrometer, what we measure, the amount of water vapor that's outside early in the morning, is an amount that's been compressed because it's non-mixed. It's compressed into a layer of air close to the surface. As the sun comes up and the sun makes its annual pass through the sky and heats the surface of the earth, the mixing depth expands throughout the day and gets quite high. And so in midday, we're mixing that water vapor into a huge volume. And of course, that shows up in our measurement of what's present. Then, of course, as the sun goes down and the wind dies off and the mixing dies off and everything compresses back into a smaller volume, that's when the dew point spikes because the water vapor content is being compressed. There are also, a lot of meteorologists argue that it's the dynamics of the atmospheric mixing that's changing as well. And that we're getting some dynamics and we're getting a more rapid compression. They argue because of elements of atmospheric circulation, we're getting a more rapid compression of the boundary layer at night, and this too is inflating the water vapor reading. So there's all kinds of working things going on here that are possible explanations, but we haven't settled on any one yet. But we've certainly been seeing these. In fact, 2 years ago, Environment Canada reported the first ever 80-degree dew point at Winnipeg. Now that's getting pretty far north for an 80-degree dew point. And that was a one-off deal. It occurred once, and it's the only report of an 80-degree dew point in Canada so far. We'll have to see if that repeats itself sometime. And again, so there's a character difference. This slide is simply to illustrate a character difference. We have in our Minnesota history books documentation of historic heat waves in Minnesota back to 1883. We have this. This has been well documented in our state history. But all of the red highlighted years are all heat waves. They're real heat waves with real consequence, but they're all about how much water vapor's in the air. Not so much the mercury thermometer reading 110 or 114 or whatever like it did long ago. So we're still subject to this type of environment, this almost like sauna-like environment, but it's really heavily, heavily driven by the water vapor content. It does have consequence. It does open up niches for certain biological organisms that love tropical-like air masses, and so they can thrive. It increases the workload in the health sector. It's caused livestock loss. Actually, it's caused real devastating in individual years, 1995, 1999, 2001, 2006. We've had pretty significant livestock loss in the state of Minnesota because these animals don't do well under this heat stress. And then it's really put a lot of stress those that have to be concerned with environmental controls. I don't know how many of you work in these buildings. We got a lot of indoor environments because of what goes on in those environments that we have to keep tightly controlled. And this is a real taxing challenge for certain areas. I don't know how many of you have been in a building, maybe where you work or live, where we've had these real heat wave spells in the summer where the dew point's so high, and you go out of your office or you go out in the hallway and you go into the exterior stairwell to go up or down a flight of stairs, and you find that the handrail is wet or the steps are wet because the water vapor is so high it's condensed on everything. And so we've had a lot more demand for finding ways to better control the indoor environment. Lastly, the precipitation is changing, and again, just like I showed you with the temperature, we occupy a region of the nation where, by the color codes here for where it's changing the most in the positive direction, we are in a region of the country where it's changing a lot. And so notably, we're having to give it more attention than some other places. If we look at the statewide average annual precipitation across time, we see this type of pattern. We see some variation here. We see the extraordinarily wet year of 2010, the wettest year of all time in Minnesota, when the average from 1,502 precipitation observers was over 34 inches that year. So very, very wet year. And we see what the seasonality character looks like. We see mixed results of above and below normal values in winter, mostly above normal values in spring, mostly above normal values in autumn, and then mixed in the summer, notably with some real dry ones mixed in recently. This is how the geography of that signature has changed. It's rather interesting. For example, if we take 1891 to 1920 and we look at what was normal, what was defined as normal across the state, we see in the light blue and dark blue geography here that these regions of the state averaged 29 inches or greater on an annual basis. Then by the time we reanalyze this in the 20th century and we incorporate the Dust Bowl era of the 30s, we see that that same quantity of 29 inches or greater has retracted to the 7 most southeastern counties in the state. Then we come out to later in the 20th century, and again we recalculate and we see that it's expanded again. And now, using the most modern normals from the 1981 to 2010 period, we see that fully half the state landscape falls in that category of annual precipitation. In other words, for frame of reference now, that's what we call normal for the area. So you can see how that's changed over time. Some of the individual site-by-site numbers have changed remarkably over time. This is how Milan has changed. Once upon a time, 21.53, now we call 2614 their normal out there in Chippewa County. We look at Glenwood, once upon a time under 21, now we call it 25.71 at Glenwood. We look at the Twin Cities here from the MSP record. It's now over 31. We look at Waseca in southern Minnesota. It's now approaching 36, one of the wetter areas of the state. And so we see upward shifts in what we call average, but relative to, certainly relative to wetlands, and I must say relative to other characteristics of our natural environment in Minnesota, we shouldn't be solely occupied with quantity of precipitation, because quite frankly, the net effect of precipitation comes from its other dimensions to its character, like when does it come, its seasonality, or how frequently does it come, or how intensely does it come, how much, how fast, or what type is it frozen or is it liquid? So we also look at all these other attributes of precipitation because they too are important. We can't tell the whole story, if you will, by simply looking at quantity. So we look at what we find, and what we find in Minnesota is a common change that's occurred in all these other landscape positions. And that is that in the western Great Lakes region, where we see that blue plus sign, more and more of our precipitation is coming in the form of intense thunderstorms. So if we dissect the 12-month year and we look at what the contribution, say, of snow and snow melt is, what the contribution of, say, mid-latitude cyclones or the big scale frontal systems that come through and give everybody a rain, and then what the contribution of summer thunderstorms, where we get the real intense thunderstorms developing over local regions and dropping a lot of moisture. It's the latter that are giving us a bigger and bigger fraction of what we get annually. And this is problematic because what does that bring? It inflates the variability. It's all about inflating the variability of precipitation. Because if thunderstorms are going to represent 70 to 75% of our total annual precipitation, then the story is going to be all about who gets it and who doesn't. And if you get in a repetitive summer pattern, that who gets it is the same storm after storm, and who doesn't is the same storm after storm, then by the time you get to the end of any one season, you've got huge disparity on the Minnesota landscape. And that's what we're seeing in the data. The instance of flash floods is increasing. You ask our state climatologist, Greg Spodger, and he'll show you all kinds of data on this. The measured and documented frequency of flash floods across the Minnesota landscape, not always in the same area, it moves around, but the overall statewide frequency is going up. It's going up in terms of the real extreme events like the 3-inch rains, the 4-inch rains, the 5-inch rains. And because of that, we've had to have the National Oceanic and Atmospheric Administration redo all of the historical hydrology statistics for Minnesota. So NOAA Atlas 14, which is now available to you on the internet. How many of you have already looked at NOAA Atlas 14? Anybody look? Great, okay. Well, you know it's GPS based, it's cursor based, so you can position it wherever you want, and then you can get all the recurrence calculations for whatever you're interested in. 5-minute rain, 1 hour rain, 1 day rain, the 100-year event, or whatever. And some of the data that's been compared, that's come out of this, is once upon a time in Minnesota, our 100-year 1-day event generally ranged between 5 and 6 inches, using the old data that didn't take into account, especially the last 3 decades of trend. Now when we take into account the data, we've got 5, 6, 7, 8 inches is now calculated as the 100-year event in Minnesota. And the other piece of the puzzle that's superimposed, if you will, on this is a very, very important piece. And it takes me a second to explain this, but I think it's really, really important. This is the work of Harold Brooks, B-R-O-O-K-S, from the National Severe Storms Lab in Oklahoma, who is the most prolific researcher on severe weather in the United States. He's been to Minnesota to lecture a number of times. I would encourage you, if you ever see his name on a program anywhere, go hear him speak. His research shows that the severe weather elements of the atmospheric structure are migrating to higher latitude. This is based on something meteorologists call the ingredients method. And as succinctly as I can say it is the following. We launch instrumented balloons called radiosondes every 12 hours. There's one that launches, the closest one here is at Chanhassen. There's one that launches at 6 in the morning and 6 in the evening with an instrument package. It goes all the way up through the atmosphere and at every vertical level all the way to about 100,000 feet. It measures the temperature, it measures the dew point, it measures the pressure, the wind speed, the wind direction, etc. So we get a profile of the vertical structure of the atmosphere. Without those measurements, we wouldn't be able to forecast the weather. So it's an absolute part of the infrastructure of the National Weather Service in this country and many other countries. In those measurements, in those vertical measurements, are certain threshold values. There are certain critical threshold values. When those values are exceeded, it pulls a trigger on an equation that gives you a severe weather element, okay? This is called the ingredients method of severe weather forecasting. When those ingredients, all in combination, wind shear, dew point, temperature change with elevation, a whole range of things, when they add up to a certain weighted value, that's when the Severe Storms Lab issues us a severe storm watch. That's how the watch warning system in our country works. And so when the ingredients methods lead to a calculation of a number that exceeds a threshold, a severe storm watch is issued for whatever geography that is that made the measurement. Dr. Brooks is finding that since the 1970s, the frequency in the vertical atmosphere that the severe weather calculation is exceeding this threshold is increasing with higher latitude position. So now we are finding ourselves in a situation where here in the Minnesota landscape, we are having as many severe weather watch days as formerly they used to have in Oklahoma and Kansas and North Texas. The ingredients are there for severe weather to develop. That's what he's finding in his research. Mother Nature doesn't always pull the trigger because, as we know, we're oftentimes under a watch, but a warning never materializes because the dynamics of the atmosphere just doesn't work out, and for some reason it doesn't come to realization. But nevertheless, this is what his research is showing. Now, this is operating in the background of our measured severe weather statistics, and we think that there's some coherent argument for this happening in Minnesota. One of the pieces of evidence we look at is the year 2010. Up until 2010, Minnesota had never led the nation in tornadoes. There was no record that had ever suggested Minnesota had more tornadoes than any other state. In 2010, we documented 113 tornadoes in Minnesota, and we far surpassed any other state. We were kind of the Oklahoma of 2010, if you will. And in fact, we had 48 on one day, June 17th. Nice day to work for the Weather Service. That was a rather stressful day. So we see that in play. That had formerly never ever happened. Never happened. Let's look further north. Let's take Dr. Brooks's papers and say, all right, now we should be seeing some symptoms show up elsewhere, not just Minnesota. If this is a latitudinal migration, let's look elsewhere. Okay, so we go to Manitoba. We look at Ely, Manitoba in June of 2007, reported the first ever F5 tornado in Canada's history with cloud tops to 48,000 feet. 48,000 feet of vertical cloud development, never observed over that part of Canada. And powerful enough convective engine to generate an F5 tornado on the ground, 261 mile an hour winds. Never ever before in Canada. All of a sudden, there in 2007. Or we go even further north. Let's go up to Hudson Bay. Let's go to 59 degrees north latitude. Let's go to permafrost territory, where you go watch the polar bears play, okay? August of 2010, cloud tops to 44,000 feet over Hudson Bay, and a convective thunderstorm complex that delivers 4 inches of thunderstorm rainfall to a permafrost landscape. So where's that 4 inches of rain going to go? So we're starting to make some, if you will, some inference about Dr. Brooks's work and looking at the latitude and looking at, well, what's going to happen to these landscapes, for crying out loud? because if severe weather does develop with more frequency at these latitudes, there's going to be some real landscape feedback. In Minnesota, Jim Zandlow, our former state climatologist, you probably heard him over the years, he documented 3 1,000-year rainfalls in southeastern Minnesota since 2004. So based on area encompassed by the storm, as well as measured quantity of precipitation, 8 inches or greater, he calculated that these were about once in 1,000-year storms. So we got the 13, 14, 15, 17-inch rainstorms over the same part of the state geography. All very devastating in their own way. Nothing compared to the granddaddy, though. History, and we always like to frame things in terms of history. If we go back to the granddaddy, we go back to the Wright storm of July of 1867, which Mr. Wright documented for us. He was out on the land survey at that time and fortunately was able to document that storm. 30 inches of rain in roughly 30 hours. So that the Chippewa River and the Pomme de Terre became basically enormous lakes. The Chippewa River got to be 4 miles wide. I've been out on the Chippewa River when I've had work out at Morris in some Julys, 1988 notably, where I could straddle the Chippewa River, you know. And to imagine it 4 miles wide is almost incomprehensible. The one and only time, based on gauged flow, that the discharge from this storm caused the Mississippi to rise by 12 feet in 24 hours and dislodge 35 million logs out of the log booms there. So we had 35 million logs washing over St. Anthony Falls in Minneapolis, if you can imagine what that must have looked like. So Mother Nature's potential for delivery of intense storms on our Minnesota landscape, this probably approximates more closely what the potential is for our region of the country. In 2012, we had this interesting phenomena of, in June, we had back-to-back flash floods. We had the second week of June, the flash flood on the Cannon River in southeastern Minnesota, which sent an all-time flow volume down the Cannon River. And then the next week, up in the northeast, we had the June 19